So I'd just like to say good morning to everybody. That's just turned 10 o'clock. Welcome to the Amatec Solid State Controls Understanding DC System Designs webinar. Going to go through a couple of things. The overview of who I am. That's going to take us a few minutes, and hopefully that will give everybody else time to join in as well. So my name is Craig Williams. I'm the Senior Technical Manager for Amatec Solid State Controls. I'm based in the Houston Stafford office in Texas. I have 20 years in the industrial UPS industry as experience. As you can tell from my accent, I'm not from around these parts. Originally, I'm from Scotland, and I had 12 years in the offshore oil and gas industry working on industrial UPS systems. And then 8 years ago, I came over to Houston and worked on industrial UPS systems in the Gulf Coast. And then 3 years ago, I started working for Amatec Solid State Controls, initially as the training manager, and now I am the senior technical manager. Basically, it means I'm in charge of all of the global service team. I've worked with all major UPS charger manufacturers, so I have a wide experience of many different makes and models. There will be a lag of around 30 seconds between when you hear my voice and when questions are asked. So we have a chat bar on the side. What I'm going to try and do is I'll keep an eye on it as the webinar goes along. I'll try to keep the Q&A session until the end of the webinar. But if something pertinent comes up during the webinar that I think needs to be answered, then I will answer that question at that time. So, but please do bear in mind there is going to be a lag from when I'm talking to when you put the question in. The platform that we're using is Webinar Jam. Originally, on our last webinar, we were using Microsoft Skype for Business, and it crashed and it didn't work too well, unfortunately. So we've spent a lot of time trying to find a good provider, and Webinar Jam seems to hit all the marks on that. And what it does is I actually have a panic button on my dashboard. So if for some reason you let me know during the chat that connection has been lost, or you can't hear me, or something like that, then I'll be able to see that, and then I can press the panic button. And what that should do is it will create a new webinar room for everybody, and it will restart the connection and hopefully prevent any issues of us getting disconnected. The webinar is going to be recorded, and you will receive a link for the recorded webinar. And the webinar should last around about 1 hour. Really, the presentation is going to take maybe 30 to 45 minutes. But depending on how many questions are asked, it could take longer, it could take shorter. Okay, so that's all that taken care of. Just want to, I suppose I should have asked this to start off. Can somebody put in the chat bar if you can hear me or not? That would be ideal. That will test that the chat system is working and that you can hear me. There we go. Absolutely. Good to see everybody out there. Thank you for taking the time out of your day to view this webinar. So hopefully you'll get something interesting out of it. So what we're going to go over today is we're going to understand the most common DC systems that are out there, understand what a DC system is designed for, discuss the advantages and disadvantages of different designs, and there are quite a few different designs out there. We're going to discuss the power flow and general operation of each of the designs, and probably the most fun part is going to be discuss common misconceptions. And then after that, we'll do a Q&A session. So first of all, here is probably the most basic DC system you can get. And what I will say to start off with is the one common misnomer is a lot of people think there's a difference between a rectifier and a charger. Okay. The definition of a rectifier is something that changes AC into DC. Okay. So a rectifier takes the AC input, usually from your MCC. So there's your AC input there. And then most chargers are going to have an isolation transformer that you can see on the screen there. And then that goes into a rectifier bridge. Okay. It can be made up of diodes, SCRs, which are silicon controlled rectifiers, or there are some modern systems out there that use IGBTs in the rectifier section. But what a rectifier does is it converts AC into DC. Now, if you add a battery to the system, that's when really it becomes a charger, because you are still using the rectifier to convert AC into DC, but you're using that DC to keep your batteries charged. Okay, so that's why the terms rectifier and charger are usually interchangeable. And then the batteries are in parallel with the DC bus, so they are always there being charged, and if anything happens to the rectifier, the batteries will continue to supply power out to your load circuits out here. Okay, so that is the most basic rectifier charger system that you can get. So if we go on to the next page, this is actually this is the ideal way to design a single rectifier battery system. Okay, so on the left-hand side here, we've got your MCC, and in most industrial charger situations, your MCC is going to supply 480 volts, three-phase, to the input to your rectifier. Now, there are caveats to that. Some people use 208. Some people have a need for single-phase inputs to their charger. But in most industrial cases, it is going to be three-phase, 480 volts, going to the charger system. Okay, so then we have our AC input terminals on our charger here, and most chargers are going to have an isolation point inside them. So we have an AC input breaker at this point here. Then that goes into a transformer. Transformer is there for two reasons. It gives us isolation between the input primary and the secondary of the transformer. We'll discuss why that's important later. And then it also allows us to step down the voltage. Now, in most industrial charger situations, we're going to be charging at a 120 volt nominal. So you're usually going to connect your charger rectifier to a 60 cell lead acid battery system. Now, obviously, there's other voltages. You can do 48 volts, 24 volts, and sometimes higher. You can do 240 volts. But in most applications, it's going to be 135 volts. Well, sorry, 120 volts nominal DC. So what the transformer does is it steps the 480 volts down to a suitable AC voltage that can then be rectified to the correct DC output that we require. And in this circumstance, like I said, if it was 60 cells, you would actually have 135 volts DC coming out of this charger. Because even though you have 60 cells, commonly in the US at 77 degrees Fahrenheit, lead acid cells are charged at 2.25 volts per cell. Always check the manufacturer's guidelines for that, but that is a good common number to base it on. So 2.25 times 60 cells is 135 volts DC. And then on the output of a charger, right here, sorry, there's going to be a DC output breaker, another way where you can isolate within the charger itself the power going out to your DC panel. So therefore, your cables go out to your DC panel, and what you're going to have is a breaker on the DC panel that will probably say charger input breaker to the DC panel. And that's between the input to the charger and the actual DC bus inside the DC panel itself. And a good design will have the battery connected through another breaker onto the DC bus, because that will give you two isolation points, and we'll explain why that's important later on. And then these other breakers here are just the breakers that can go to your load circuits. Okay, so this is a really good design, because what you can do in this circumstance is you can isolate the charger at this point here, and you can still have the battery online feeding the load circuits, and you can do maintenance or even replace the rectifier while you're still supplying load with the battery. And vice versa, you can also open the battery disconnect. You can, if you're going to do a capacity test on the battery, you can connect in a temporary battery, disconnect the existing battery, and then close that breaker, and you can do a capacity test or even maintenance on the battery as well. So it's very good, gives you many options. So what's not a good design? Well, a lot of people will look at this drawing here and say, well, there's not much difference between what I'm saying is a good system design and this one here where it's saying not a good design. And the difference in this one here is they haven't connected the battery here directly onto the DC bus inside the DC panel. What a lot of people, well, not a lot of people, but what some people do is they actually connect the load cables and the battery cables to the output terminals of the charger. Now, for me to explain that, I'll go to the next slide and you can see what I mean. So here is the DC output from an Amatec solid-state controlled charger. And you can see here, they have the load cable connected via a lug on the front of this bus bar, and they have the battery cable connected on the back of this bus bar. So they have connected the load and the battery cables in parallel. This is absolutely fine. It will work. But what happens if you need to do maintenance on the charger? If something goes wrong with the charger and you need to do maintenance on it, then what you're going to have to do is you're going to have to lift this lug here. You're going to have to undo this bolt and disconnect this lug. And if you do that, you're going to break the circuit between the battery and the load cables, which will drop power to your load. So that is not a good system. So you shouldn't do that. And the other one that's not a good design is if you connect the load cables and the battery cables at the battery itself. And another example of this is here. So the top cable on this picture here is from the charger. Okay, that's supplying power to the battery. What some people do is they will use this additional hole on this plate on the main positive connection, and they will attach their load cables there. And you go back to the same situation where if you want to do maintenance on the system, which could involve removing these bolts here and removing the plate completely from the battery if you want to replace the battery, then you're going to have issues. So it's much better to follow the design and have the battery go through one breaker to the DC panel and the charger go through another breaker to the DC panel. I hope that was clear. Once again, remember, if you have any questions, just type them in the chat bar on the side and I will go through them as we go. So that's what not to do. And also, here's another example of a battery. Once again, the bottom, this cable here is from the charger. If you connect your load cable to this side of the lug, then you're going to be in exactly the same situation. If this bolt ever has to be undone for any reason, you want to maintain power to the load circuits, whenever you undo that bolt, you are going to lose connection and you are going to drop your load circuits. So not a good design. So what we discussed earlier was for a single charger. So you can also have a dual parallel system. And this is one way that you can connect a dual parallel system. You've got two identical rectifiers. So say, for example, the spec for this system was you needed 100 amp chargers. Okay. For a dual parallel redundant system, you would have to install two 100 amp chargers, because if one fails, then the other one can supply the full 100 amps if necessary. Okay. And then you can see here that our load cables are going out onto separate disconnects on the DC panel. And in this system here, they only have one battery. Okay, so they have two parallel chargers, but they have one battery. And another important thing to remember when you're designing systems that have parallel redundant chargers, if at all possible, this has MCC1. So my advice to anybody is for MCC1, feed that from your emergency board, okay? One of your MCCs that's backed up by an emergency generator. And then, if at all possible, feed the second charger from a different board. And what that allows you to do is, say, for example, you're doing maintenance on MCC1, then you still have power on MCC2, and you're still keeping at least one charger powered up while you're doing maintenance on one of the MCCs. Okay. I know sometimes it can be difficult because there may not be another MCC that you can pull power from, but if at all possible, use a different MCC, motor control center, to feed each individual charger in a parallel system. Okay. Now, this is identical to the picture before, but in some highly critical DC systems, they may not have a disconnect for the battery. The battery may be connected directly onto the DC bus. And a good example of this is DC lube oil pump systems for turbines. They don't want anything to interrupt power from the battery. They want to run basically to destruct when you're trying to protect the bearings on a very expensive turbine. So they may remove the disconnect and connect the battery terminals directly to the positive and negative of the outgoing bus in the DC panel. So keep that in mind if you are designing a very highly critical DC system. Now, this one here gets the yellow gold star. We have two dual parallel chargers fed from hopefully separate MCCs. And in this circumstance, what we have is we have two batteries, each with their own disconnect. So we have battery 1 and battery 2. This gives us complete redundancy for all parts of the system. So, for example, if rectifier 1 failed, then rectifier 2 will carry on supplying the load circuits and feeding both batteries with float charge current. Okay. And let's say battery 2 fails. Well, we still would have two chargers and one battery remaining. Or if you wanted to do a capacity test on battery 2, you could just open this disconnect here, and you could do a capacity test on battery 2, and battery 1 would still be online, keeping backup power to your DC panel if necessary. So this, although obviously it is the most expensive design, but it is by far the most robust design, and I would recommend anybody, if at all possible, if you have the budget to do it, this is the ideal design of a DC system. Okay. So the power flow for a normal single rectifier charger system. The green line is the normal current flow, okay? So your 480 volt MCC supplies power to the AC input to the rectifier. And as you follow that green arrow, that AC gets converted into DC, and then the DC goes to the DC panel. And then the charger will carry all of the load current in normal operation. So all your loads are being fed from the charger. But please, I'm going to stress this a little bit later on. The battery is in parallel, okay? So it is being trickle charged. It's taking the suitable amount of current for it to stay at its fully charged state, okay? And that trickle charge current, when it is fully charged, is very, very small, usually anywhere between 2 to 500 milliamps. It's usually less than an amp, unless you have a very, very large battery. Okay, so the battery is just being trickle charged in normal operation, and it's the charger that supplies current to all of your load circuits. Okay. Now, if you have a power failure at your MCC, the 480 volts disappears. And a lot of people say, well, okay, at that point there, we switch to battery. We never ever switch to battery. There's no switching mechanism that happens. My analogy usually is it's just like a laptop. When you've got your laptop plugged into the AC outlet, everything works fine. And if you pull that AC outlet out, nothing switches. The battery is just there in parallel. So as soon as the power from the charger rectifier goes away, the battery just continues to supply power to your load circuits seamlessly with no switching whatsoever. So as you can see here, the green is now the current flow. So the green is coming from the battery and going out to your load circuits if you have a power failure. So if we then, the power comes back onto the MCC, and what will happen is the rectifier charger will start up immediately. There should be no need for any interaction between plant staff, electricians, or anything like that to get the charger back online. The charger should come back on automatically. It will start supplying power to your load circuits again. So these green ones here, the charger is now supplying power to the load circuits. And then you can also see here, now full recharge current is going to the battery, okay? So whatever the system is designed at, however much current is left over from the charger after feeding the load circuits will all go into the battery to get it recharged as quickly as possible. Okay, so somebody's saying the voice is very low and hard to hear. Hopefully that's not the case for everyone. Is anybody else having issues with the audio? I just have to wait for the lag. Nope. Good. Thank you, Jacob. Cool. So for Fu Hong, maybe it's something to do with your computer settings itself. Somehow you may need to turn the volume up. Okay, so the normal power flow for a dual parallel system, you have two charges in parallel. So MCC1 and MCC2 will feed 480 volts to each charger, and both charges are connected in parallel. So they will feed the load circuits, and they will also keep both batteries trickle charged. Same principle as what I discussed before. Now, if one charger fails, or if the power to one of the MCCs fail, then the other charger will just carry on as if nothing happened. It will continue to supply power to the load circuits, and it will supply the trickle charge needed for both batteries. It won't be an issue. One charger can charge both batteries. There's no issues there whatsoever. But you do have to keep in mind that there's still going to be DC at the output terminals of rectifier 2, because we're saying rectifier 2, the power has gone out at the MCC. But do remember that there is going to be power at the output terminals of rectifier 2. So if you are going to go and troubleshoot rectifier 2, or maybe even replace it, you do have to remember to go in and open this breaker here, and that would prevent any backfeed from the DC bus that way back into rectifier 2. Okay. And then if the other charger fails, or both MCCs, we've had a complete power outage in the plant, then both rectifier charges are not going to be supplying power anymore. all of the current for your load circuits are going to be fed from battery 1 and battery 2. And they're going to basically share the load and feed the load circuits for whatever the designed criteria of the batteries are. Okay. I don't know what that's going to be because I don't know what the design of your system is. That's something that your design engineers have to work with. They have to look at the load currents and figure out what size battery they need for what time of backup they need, if that makes any sense. Okay. Now, this picture here shows what you can do, why this system is such a good system when you have a dual redundant charger system. If you have a problem with rectifier 2, so let's say rectifier 2 has failed, let's say they're obsolete and they're not made anymore, you can't get parts for that rectifier anymore, and you know you're going to have to replace rectifier 2, then what you can do is you can apply a lockout tagout to MCC to the 480 volt supply. And then you can also apply a lockout tagout to the DC breaker in your DC panel. Okay. And that means there is going to be no power on the AC input terminals to rectifier 2. There's going to be no power on the DC output terminals to rectifier 2. So you could go in there, you could disconnect the cables on the AC input, you could disconnect the cables on the DC output, and you can just remove rectifier 2 and install a brand new rectifier. All while the power is still being fed through charger 1 to your load circuits. So you can do this online without any issues whatsoever. It gives you so much flexibility. You can even use this for maintenance purposes. And in truth, I'm going to get onto this a little bit later. Let's say this is an obsolete rectifier. Let's say they're both designed in 1980 and you can't get exactly the same rectifiers anymore. I'll discuss this later, but you could, in theory, get a different model of charger for rectifier 2 as long as it has the same output current as rectifier 1. And you could install a different rectifier here, and you could have them both run in parallel as long as they are rated for the same current. Okay. I hope that's clear. I really, really think this is the best design of system. Once again, it is a bit more expensive, but it is definitely the best design. Okay. Now, the other great design of this, obviously, batteries have to be tested on a regular basis. IEEE 450 and all the other applicable standards apply. And if you have a wet cell battery, usually you're going to have to do a capacity test on that battery every 4 to 5 years. That's a maximum duration. Sometimes you have to bring it in a lot closer than that. And plants may have their own routines that they go through, but you are going to have to capacity test a battery every 4 to 5 years. So what you can do in this situation is you can apply a lotto on battery 2's disconnect. You can see this arrow here. It says lotto here. You can open that disconnect, tag it out, and then you can have somebody, an external company, or if you have load banks yourself, you can come in and test battery 2. You can do a full capacity test on that battery, and you will still have both chargers feeding the load circuits, and you will have battery 1 still on charge. So if something happens during the test, you're still going to have a battery available to supply power to the load circuits while battery 2 is being tested. Okay. And then once battery 2 is tested, you just remove the lockout tagout, close this breaker back in again, and the chargers will recharge battery 2 up to its full charge level without any issues whatsoever. Okay. So I hope that explains most of the DC system designs that are out there. So the typical uses for DC UPS systems, because they really are still a UPS, because a UPS is classed as an uninterruptible power supply. And anything that has a battery backing it up is basically an uninterruptible power supply. So it's called a DC UPS. So really, for the oil and gas industry, the most typical application is going to be a switchgear tripping and closing supply. The DC charges the springs, controls the solenoids and mechanisms that cause the tripping to happen, and it also keeps the power maintained on all of your electronic tripping curve circuits. That's probably not a good way to explain it, but all of your electronic tripping and closing controls, the DC will keep those powered up as well. Okay, and it's very, very important that those tripping and closing springs can be charged and discharged, and the switchgear can disconnect power when there is a power outage, because if there is a fault when all AC power has been lost, those batteries are critical to allow that fault to be cleared and not cause a fire on your MCC. The other use for DC systems is a DC lube oil pump on turbines. Once again, that is absolutely critical. You know, you have a million, I don't know how much turbines cost these days, to be honest, but it's multi-million-dollar turbines, okay? And what the DC lube oil pump does is, if you do have a power failure and the turbine has to be shut down in a controlled manner, the DC lube oil pump will supply power to the pump that keeps oil flowing through the bearings as the turbine slows down and comes to a halt. And if that pump loses power, then the turbine bearings are going to fail because they're going to overheat, and then the shaft of the turbine is going to be warped, or it could even break, and that would be a huge expense to anybody. So DC lube oil pump batteries are extremely important. Common offshore, you have DC powered DCS systems, distributed control systems. Basically, on a lot of offshore installations, rather than have that fed from an AC UPS, they will take a 24-volt DC battery and a battery chargers, and they will use 24 volts DC direct to their DCS system to keep their DCS system powered up. So they have complete overview of the plant process. Okay. Also, telecommunication systems, broadband, cell phones, all these kind of systems have to have a backup system, and that's usually either a 28 or a 48 volt telecommunication system that backs those up. And there are also some instrumentation requires DC power. There could be some solenoids out in the field, or some sensors, transducers. Sometimes they work off DC power. So that list is not limitless. There are many other things that use DC power that I haven't listed there, but that's how critical DC power can be in the plant situation. Okay. So here's my favorite part. Common misconceptions. Now, obviously, I can't go over every misconception. The 5 that I've listed here are the most common that we hear at Amatec Solid State Controls on a regular basis. Okay. So the first one we're going to go over is, my battery voltage is 135 volts. Therefore, my battery is good. I'm going to just take a drink, one moment. So that couldn't be further from the truth. So what I want to do is try and give you an idea of why that is not true. So you can see in this drawing here, we have the 120 volt supply that comes into your house normally. Okay, so that's your 120 volt AC supply that comes into your house. Let's say you have 3 lamps. Okay, there's lamp 1, lamp 2, and lamp 3. Okay, let's say one's in the kitchen, one's in the dining room, and one's in your living room. Okay, all of those lamps are connected in parallel. Okay, so as you can see here, if you measure across the power going into any of these lamps, you will measure 120 volts AC, because this point here is exactly the same as this point here, because they're in parallel. Okay? So hopefully you're following me on this. Now, let's say the third lamp, this one that was here, fails or is even removed. We've still got the terminals to the lamp at these 2 points here. And if you took your fluke meter and you measured from that terminal to the other terminal, you're still going to measure 120 volts AC, even though that lamp is not there anymore. Okay, because they are in parallel. So let's switch it round. Let's say you have a charger that is supplying 135 volts DC. And let's say you have 3 batteries in parallel. Exactly the same situation as the AC, but now we have 3 batteries in parallel. If you took your fluke and you measured this point here to this point here, you're going to measure 135 volts DC. So hopefully you're following me on this. Now, if we remove one battery and we still measure at the terminal that was going to this battery and was going to this battery, you're still going to measure 135 volts DC, because they are in parallel not only with the other 2 chargers, 2 batteries, but with the charger as well. Okay? So now we remove all the other batteries and we only have one battery connected. So we've got our charger here, 135 volts out. And with the battery there, we measure 135 volts from the main positive, this point here, to the main negative. Hopefully you're following me. So now, let's say that battery disappears. We don't even have a battery anymore. But if we took a fluke and we measured the terminal, the positive terminal going to that battery and the negative terminal going to that battery, because this charger is here and they were in parallel, you are still going to measure 135 volts DC, even though there's no battery there. So for somebody to say that I'm measuring 135 volts at my positive terminal and my negative terminal means that my battery is okay, hopefully you can now see that that is not the case, because you could remove that battery. You're still going to measure 135 volts DC, because that's actually the charger voltage. Okay? And the most obvious failure that can happen, obviously you're not going to remove a battery and expect your battery to be okay. That's rather silly. But if you have an open circuit in that battery, it is as if that battery is not there, because power cannot flow through that battery or from that battery. Okay, so if you have an old battery that has an open circuit cell in it, it is as if the battery is not there. But you're not going to know that the battery is not there, because if you just measure on the positive and the negative of that battery, you're going to see 135 volts, because that comes from the charger. Okay? The only way you're going to find this open cell is if you do regular battery maintenance and you use either a cell coder to check the internal resistance of each battery cell, and that would detect the open circuit cell, or if you did a capacity test on that battery and you would find it out. So never ever think that just because you have 135 volts on the positive and negative of your battery, that means your battery is healthy. It couldn't be further from the truth. I hope you understand now why that is the case. The only way that you can absolutely say that your battery is healthy is to do a capacity test on it. Even using a cell coder to do internal resistances, it will find most issues, but it might not find all issues. Capacity test is the only way to absolutely find out if your battery is fit for service. Okay. Our next situation, let me just do one thing, is I can disconnect my battery while I am online. Once again, it is a misconception in many different circumstances. Okay, and let me explain why you shouldn't have that attitude. Okay, so in normal operation, our charger is feeding the load circuits. Okay, and we are keeping the battery on trickle charge. Okay, so if we, I'm not going to get into exactly how a charger operates, but basically what it does is it rectifies the AC into basically this purple waveform here, okay? And then, because most chargers have capacitors in it and batteries also have some capacitance in it as well, the mathematical average is this line here, okay, which in our situation would be 135 volts DC. So this line here is at 135 volts DC. That's what keeps our batteries charged and feeds our load circuits. So try and follow me with this. So if we remove the battery, if we disconnect the battery to do some maintenance on it, okay, if this charger is an older charger and it does not have a capacitor bank, a filter capacitor bank inside of it, what's going to happen is the capacitance of the battery, and when I say capacitance, I mean actual two plates connected, sorry, not connected, two plates very close together, separated by a gap, becomes a capacitor. Okay, so we've removed that capacitance internal to the battery that was smoothing out the DC, remember, to that line that was round about that value there. So if the charger doesn't have capacitors itself, your load circuits are going to see that blue waveform. They are going to see, we call it a pulsating DC waveform, okay? And if you obviously see at this point here, it goes down to 0 volts. And at this point here, it goes down to 0 volts. And some of your load circuits, because it's not full DC anymore, some of your load circuits may drop out because of that, okay? And also, this peak of the waveform is higher because there's no capacitance as well. So that peak may actually cause some damage, some overvoltage damage to some of your equipment as well. So to say that you can remove the battery from a system and allow the charger to maintain the load is not correct in all circumstances. And you have to be very, very careful when planning work on batteries if you know you have a charger that doesn't have capacitance in it. Okay. The other reason why you can't disconnect the battery, so in this picture here you can see we've got the lotto applied to the battery breaker here, is in some circumstances, in many circumstances, the charger is usually sized for the recharge time of the battery. Okay? So when the design engineers were working out what size charger they need and what size battery they need, they looked at the load circuits, how long they needed to be maintained for if there was a power outage. And in this situation, we're seeing here that the design engineer chose a 100 ampere hour battery. Okay? So they then decided, okay, we need that battery to be recharged within 8 hours. What size charger do we need to recharge those batteries? And they did their calculations and they said, okay, to get the batteries charged up, fully charged, so it's more like 90% charged in 8 hours, a 30 amp charger would be suitable. Okay. Now, obviously, they have to try and save cost. There's no point in putting in a 100 amp charger that's a lot more expensive when a 30 amp charger would do exactly what we require. So remember, they put in a 30 amp charger, and that is solely to recharge the batteries back up in 8 hours. Now, if you remove that battery, we only have 30 amps available from this charger rectifier here. And let's say we are supplying switchgear tripping and closing circuits. That means the charger can only supply 30 amps to any load circuit or all load circuits at any time. So a common charge motor inrush for spring coils in a switchgear tripping and closing system is between 20 and 30 amps. So let's say 3, 4, maybe 5 breakers need to trip at the same time. That could be anywhere between 100 and 150 amps that is required to trip or charge the springs in those switchgear. And a 30 amp charger isn't going to cut that. It's going to go into current limit. And then with it going into current limit, what happens is the only way it can limit the current is to lower its voltage. And in doing that, the voltage is going to go down, and therefore that's going to affect all the other DC loads it's connected. So it is an absolute, it's absolutely incorrect to say that you can disconnect a battery to do work on it, leave your charger online, and everything will be okay. That is not the case. It is such a common misconception. And there's a lot of manufacturers that go out and they sell a charger called a battery eliminator. Okay? There is no such thing as a battery eliminator. It's just, there's nothing that can replace a battery. When companies say that a battery eliminator, all they're saying is that this charger here has a large amount of capacitors in it, and it can maintain the load circuits if it's rated for the full load of this DC panel. That's what they're saying. But in truth, do not run your DC system without a battery if at all possible. If you need to take your battery out of service, get with a company who can supply you with a temporary battery. Connect a temporary battery in, remove your faulty battery, and then tie in the temporary battery onto your DC panel. That is the best way to do it. So that's number 2 of the common misconceptions, that you can remove the battery. Just don't do it. That's my my advice. Okay, the next one is the ground fault is on my battery charger. Oh, we hear this all the time. Now, there are obviously some situations where the ground fault could be on the charger, but 99% of the time, the ground fault is always on a load circuit somewhere. And I'm just going to go through this and explain how the ground fault detection system works and why this is a common misconception. Okay. So, as you can see in this slide here, we have an isolation transformer on the input to the rectifier. Okay. And that input transformer is very important. Now, I'm not going to look at a 3-phase system. We're just going to look at a single-phase system, so it gives you an easier understanding of what the transformer is doing. So if you had a charger that took 120 volts single phase into the input of the transformer, okay? So this top terminal here is the hot, and this bottom terminal here is the neutral. Now, back at your MCC that is feeding this, your neutral is going to be connected to ground. It's going to be bonded to ground. Okay, so the neutral here is bonded to ground. But then you can see from this transformer, there is absolutely no electrical connection between the primary here and the secondary here. Okay, so let's say this is just a 1-to-1 transformer, 120 volts in, 120 volts out. Okay, the secondary is classed as a separately derived source. And what that means is it has no electrical connection to the input, the primary. So this neutral down here has absolutely no connection to ground whatsoever. Okay, it's floating. Hopefully take a moment to take that in. Okay, the primary neutral is connected to ground, but the secondary neutral has no connection or reference to ground whatsoever. So if you took a fluke and you went between the hot on the secondary side of this transformer with reference to ground, what voltage would you expect? Well, obviously on the screen here, it says there is no reference. So there should be, in an ideal world, there will be no voltage because there is no reference whatsoever. But due to the way that electricity works, and nothing is ideal, there can be some stray capacitance and other things that can give it a ghost potential. In other words, a false reading. What you will see is if you do get a false reading, and if you do connect your fluke to the positive here and to ground here, let's say it starts off at 60 volts DC, and what you will see is you will see that slowly discharge through your fluke meter, because your fluke meter is discharging that ghost potential. And the longer you keep your meter on, it will eventually go down to 0 in most cases. Okay, hopefully you understand that. And then it's identical for the if we put a charger on the secondary of that transformer. Okay, so now let's look. I'm going to go back to that screen. So we have our secondary of the transformer here. Okay, so the next slide, we still have the secondary of the transformer here. Remember, we've got no connection to ground down here. And then we are taking that AC and we're putting it through our rectifier charger here. Okay, so that means there is still no reference if we go on the positive of the battery down to ground. Once again, there could be stray capacitance and other things giving a ghost potential. So if you go between the positive and the battery rack, which should be connected to ground, there should be no reference whatsoever. You should, in an ideal world, see 0 volts. Okay, and that is the same for the negative to ground. There should be no reference. Now, I know a lot of you are saying at this point here, if you've ever put a fluke onto a battery system, you're saying that's wrong. Every time I go on a battery, it shows me half the battery voltage. So for a 60 cell system, it would show you 67 volts positive to ground and 67 volts negative to ground. Well, there's a good reason for that. Okay. We need to know if there is actually a ground fault on the output of this system. And what happens is most charger manufacturers are asked to create a ground fault detection circuit. Now, the most basic, and this goes back to when charger ground fault circuits were first designed, the easiest way to do that was just to connect 2 lamps, okay, in series on the output of the system, and then they tie the ground point to the midpoint of those lamps. Okay, now bear with me here. Let's say there are 120 volt 5 watt lamps. So that means they're approximately 3K ohms each. Okay. So the important thing to remember here is 2 resistors in series of the same value create what's called a potential divider circuit. Okay. And that potential divider circuit has a ratio of 50-50 if the resistors are the same value. And we said that they were in the last one. So we said they were like 3K. So what that does is it ties an artificial reference to this ground point here through these lamps. And because they're in series, the voltage is split with a ratio of 50-50. That is why you get 67.5 volts from positive to ground, and you get 67.5 volts from negative to ground. The charger ground fault detection circuit has given you that reference. It wasn't there before until we created this circuit. Okay. So I'm guessing you're probably saying, well, okay, how does this circuit work then? Well, what happens is, if there is a ground fault, so let's say the positive has shorted to ground somewhere. Let's say there's a leak on the main battery and some electrolyte has leaked from the positive post to the battery rack, and the battery rack had some of its paint had come off, and the positive is now connected to the rack through the electrolyte. Then you're going to have pretty much a direct short between the positive here and ground. Okay, that means there's going to be no potential between positive and ground anymore. It's going to be 0 volts DC. So this lamp goes off. Okay, but guess what? Now we're going to have 135 volts across this lamp. So this lamp now is going to go very, very bright, because in the previous slide, in the previous slide, the lamp was only dimly lit, and now this light here is fully lit, and that indicates that you have a positive ground fault on your system. Okay. Hopefully me minimizing my screen there hasn't made your presentation look weird. It hasn't made my presentation look weird, but hopefully we can carry on regardless. Okay, so as I said earlier, ground faults are nearly always caused by circuits on the load side of a DC panel. So any fault on the load will be indicated as a ground fault in the charger because they're connected in parallel. Okay, so any ground fault, so you can see here, here's a ground fault on this circuit here. Okay, any ground fault on that circuit will show a ground fault inside the charger itself. So if you are in a situation where you have a ground fault on your system and you don't know where it's coming from, the first thing I always recommend our clients to do is open the rectifier output breaker, the charger output breaker here. Okay, obviously you still need to make sure that your battery is connected. You have to make sure your battery is connected. Okay, and then if you open the battery disconnect, sorry, the charger disconnect here, that removes the ground fault detection circuit from the system. Okay, and then what you need to do is go from your positive on your battery to ground and from your negative on the battery to ground. And if you still have a ground fault, that means the fault is not in the charger. It means it's on one of your load circuits. Hopefully you understand that. And then once you have found that the problem is on your load circuits, you have two options. You can use what's called a ground fault detection device. Mega make a really good one. A grouser is what it used to be called. And what it does is it injects a signal down a ground fault path, and you can use a sensor to try and connect which circuit that has the ground. Or if you have the ability to open the load circuits, you have the ability to power down the load circuits, what you can do is open each load circuit individually, and when the ground fault on the battery goes away, you know that that circuit is what is causing the ground fault. Okay, so hopefully that explained ground faults. And like I said, 99% of the time, it's always something like a transducer out in the field, or some fault inside an MCC on the DC bus. It's very, very rarely that the problem is within the charger itself. It's either the battery with leaking electrolyte, or it's on a load circuit itself. So the next one, my parallel chargers are not sharing the loads. Excuse me if I laugh. What's wrong? Okay. What's wrong? Nothing. Probably. There's always a caveat. There's always a caveat to it. But this is really the most common misconception, that parallel chargers must share the load. That is not the case. Okay. So the most important thing in any charger system is that the float voltage of the battery is kept to what is required at 77 degrees Fahrenheit, or whatever your switchgear room is, or wherever your battery is. Okay, at 77 degrees, most lead acid batteries need to be charged at 2.25 volts per cell. So that means you have to have 135 volts at the battery terminals. Okay, I hope you understand that. It's 135 volts at the battery terminals. Now, you have two rectifiers here. They're going to be probably very close to each other in a switch room somewhere. But, sorry, let me just put my whiteboard back on again so I can show you. 2 seconds. This cable here, the output cable to the DC panel from charger 1, might not be the same distance as the output from charger 2 to the DC panel. And depending on where the batteries are located, you can see here the cable going to battery 1 is much longer than the cable going to battery 2. So obviously cable has inherent resistance. The longer the cable, the more resistance there's going to be. So if you set the output of the charger at the output terminals of a charger, you set the charger 1 to be 135 volts here and charger 2 to be 135 volts there, then because of the cable drops, when you get to the battery, that battery here might actually be 134.5. And this one here might be 134.9. Okay, so they're not being charged at the correct voltage. So vice versa, if you set the terminal voltage of battery 1 here to be 135 volts, and this battery 2 here to be 135 volts, you might find that rectifier 2 output is maybe 135.5 volts. And this one here is 135.1 volts. And whenever there is an unbalance between the output voltage of rectifier 1 and output voltage of rectifier 2, whichever has the highest voltage will supply the majority of power to the load circuits. They're in parallel. Whichever has the highest voltage is always going to win. Okay? So that is the inherent problem with load sharing. Load sharing doesn't take into consideration the battery terminal voltage. Okay, if it did, then it would cause an unbalance and you wouldn't be able to share the load. So in most cases, when you have forced load share between two battery chargers, it doesn't really work very well. And another example of that is, let's say rectifier 1 has a higher voltage, then rectifier 2 is not going to supply the power to the load circuits because rectifier 1 has the higher voltage. It's going to supply more of the load. Okay. Also, it's got to be noted that the charger circuitry to force a load share is inherently very poor at less than 10% of rated load. That goes for nearly all manufacturers. And in most circumstances, you'll find that most chargers are very lightly loaded. It will be below that 10%. So the forced load share is not going to work very well. Also, if you have a charger that has temperature compensation, then the load share circuitry does not work well with that because one battery may be warmer than the other battery, and that causes issues. And then forcing load share can cause issues with the battery being over or undercharged, just because of the volt drop in the cables that I mentioned before. The best idea is to set the output of both chargers at exactly the correct float voltage for the battery. So you go to battery A and you set the charger A to 135 volts. You go to battery B and set it to 135 volts, and then just leave them. Then they should work absolutely fine. okay? And then if you have a concern that one charger doesn't work because it maybe has a slightly less voltage than the other charger, then what you can do is just press the equalize button. And then if the charger starts to supply current at the higher voltage, all is good. And then you just put it back to float. Okay. It's one of my pet peeves, forced load share. There's absolutely no reason for it whatsoever. A lot of people will say, okay, well, if I don't see current on charger 2, then I think that it is broken. Well, like I say, just press the equalize button and then see if it takes over charge. And if it does, the charge is absolutely fine. And I think this is the last one. My switchgear charger has no or low current. Okay. Now remember, for a switchgear system, the only load on the switchgear system in normal operation is auxiliary circuits, such as lamps and very light loaded things. The total load may be anywhere between 2 to 5 amps. Okay. The trickle charge for the battery is going to be very small as well, depending on the size of the battery. It's going to be usually milliamps. So on most circumstances, the load on your switchgear system is not going to be any more than 2 to 5 amps. And sometimes if you have an analog meter, that's not going to show very well. And even with digital systems, when you're down in the mud, down in the 0 to 5 amp range, sometimes just inherently the way that we measure DC current, you can get some inaccuracies down there, and it may look like that you don't have any load, but it's not a problem. As long as the charger is on and the battery is connected, that doesn't mean that there's a problem when you see light load on a switchgear system. Okay. So that's the end of the presentation. I see nobody has really asked any questions during the presentation. That's been an hour. I'm still available for the next 15 to 20 minutes. So now, if you have any questions that you would like to ask about the presentation, I'll leave it open for 5 minutes. If we don't get any questions, then I will just finish the webinar. So now's your opportunity. Type it in the chat bar if you have any questions. And obviously there's going to be a delay, so give me a chance to catch up if you do. So we'll keep this open until about 12 minutes past 11 for all your questions. And if you don't have any questions, obviously this is the end of the webinar, so you can go off. You will be sent a link. If you do log off, before you do, we are going to be sending out a survey to everyone to ask what you thought of the webinar, what you think we can do better. And also, don't forget that Amatec solid state controls, we offer training. If you go to our website, you can come to our facility in Stafford, Texas, and we offer what we think is the best training that you can get on live systems. We have a huge lab that has many different types of our UPSs, batteries, and charger systems. And if you're looking to sign up, then you can go to our website and you can sign up there and we can take care of you. Hopefully the coronavirus hasn't affected you guys too much. I know it's causing a lot of issues all over the world, and I know we have to take the correct precautions, but hopefully it's not affecting you too much. Okay, so we have a question. If removing the batteries out of a single system can cause damage, how do you do battery maintenance while online? It's a very good question. Most of the battery maintenance that's done with the battery online is with a cell corder. And the cell corder doesn't need you to remove the batteries from the system. It does an internal resistance check with the batteries being online. It basically injects current through each individual cell and then measures the volt drop across the positive and negative of each cell and determines the internal resistance of that cell itself. So you don't have to disconnect the battery to do that sort of maintenance. But if you are going to be doing connection, if you're going to be tightening or loosening connections, or if you're going to be doing a capacity test, the only way you can do that is to get a temporary battery from the person who's going to be doing the maintenance. They can connect that, they can temp into the system, and then remove the battery that's being tested from the system while the temporary battery is taking care of the load circuits. Now, do bear in mind, you must use a reputable company to do that, because they have to look at what the ampere hour of the battery that is being maintained is. So say it's a very large 1000 ampere hour battery, then they are going to have to come in with a very large 1000 ampere hour battery as a temporary, because you have to be in a situation where if the power goes off while you're doing testing, that battery has to be able to fulfill its needs. Okay, so thank you for that question. In the comment section, if you are looking for the training, Brooke has put in a link to the training in the chat bar, so you can use that to go to our training website. Any more questions? I hope that answered your question, Skip. Okay, here's another question. Does sharing the load between inverters work the same as chargers if they don't share equally? Very good question. No, it doesn't work the same. Inverters are far, far more complex than chargers. And what that does is it means we have to have very detailed control circuits. And with AC, with DC, all you're dealing with is resistive loads. Okay, you don't have to deal with power factor. But with AC inverters, you're dealing with power factors, leading loads, lagging loads, inductive loads, capacitive loads. And that all affects load sharing. And you have to have very complex electronics to be able to figure all of that out. Because if you don't, then you can have problems where one UPS will actually feed circulating current into the other UPS if it's not designed correctly. So excellent question. The load sharing between inverters is usually very, very tightly controlled, and it should be, let's say the total load is 60 amps, then you should have 30 amps on each system, if not 25 and 35. They should be very close, but great question. Okay, while we wait for any more questions, I just want to say that we will probably have our next webinar in a month's time, a month from today. If you have any suggestions for what you would like that webinar to deal with, please let us know. You can go to our website, contact the service email. It's service@amatec.com. And if you have any topics that you would like us to cover, then we would love to hear what you have to say. Okay, we've got another question here. We use DC systems a lot, and when they read the spec of the battery and the battery charger, what information is needed to know, like input and output power, ampere hours, and everything? It's actually a very difficult question. Basically, the first thing that you need to know is you have to get a load schedule of all of the DC loads that are going to be connected, and you have to work on a worst case scenario. Okay, so let's say that worst case scenario is if every load was on, you need to have 100 amps. Okay, now most people are going to be very cautious. So what they're going to say is, okay, if every load is on, I need 100 amps. I'm going to put in some error there. So they're going to say, okay, I'm going to add 150%, sometimes 200%. So they're going to say, okay, worst case scenario, I'm going to say it's going to be 200 amps. And that gives me some room for expansion as well. So let's say all the load circuits are 100 amps. You say, okay, but my system needs to be able to supply 200 amps. What that does is now you know how much current you have. Now you have to work out how much time do I need to supply that 200 amps for? What is the specification from the customer? So let's say the customer says, I need my load circuits to remain energized for 3 hours. Okay, that gives them enough time to shut down valves, do whatever is necessary. So they say 3 hours is what I need to backup time. What that does is it gives you your two set points now. You need 200 amps and you need it for 3 hours. So what you then do is you go to the battery specifications. Basically, you can go to the reputable manufacturers out there, Enesis, C&D, Penn State, whoever it is, and say, okay, I need a battery that is going to supply 200 amps for 3 hours. And then they will give you what they think is the best battery model that they have. So that's the battery taken care of. Okay, the manufacturer will do those calculations for you and say, okay, it should be, let's say it's an Enesis. Let's say they say it's a 3cc11 or something like that. Okay, that's the battery taken care of. Then what you have to ask the battery manufacturer is, okay, well, actually you have to ask the client, how quickly do you want the batteries to be charged back up again after a complete power failure and the batteries have discharged fully? So most plants have it in their specs that it has to be charged within, let's say, 8 hours to 80% capacity. So therefore, you go to the battery manufacturer and say, okay, how much current do I need to supply back to the batteries to get them charged back up again in 8 hours? And the battery manufacturer will say, okay, you need 50 amps. So therefore, that tells you what size your charger should be. Your charger is only there, remember, to keep your batteries charged. So you can put a 50 amp charger onto a battery that is designed to supply 200 amps for 8 hours. As long as those three things that I mentioned, the backup time required if you have a power failure, and the recharge time, once you know those, that's what you need to know to design the system correctly. And what I would say is most of the manufacturers will help you with all of those calculations if you just tell them what the spec that the client is looking for has. Hopefully that answers your question. Okay, I think that's about all we have time for. I don't know if I close the room, if you can still ask questions. When we send you out the link for the survey, and also we're going to send out the link for the recording of this webinar, it may well give you the opportunity to ask more questions when you're watching it again, and I'll get those questions and I can answer them personally via email. So if you have any other questions that you want to ask, that is a possibility as well. So hopefully everybody got a lot out of this presentation. I hope it was interesting. I hope you learned at least something. And I really appreciate you taking the time today to listen to this. And hopefully you will join us for our next webinar, which should be in a month's time. So remember, if you have any topics, let us know, and we'll see if we can take care of you. But from everybody here at Amatec Solid State Controls and myself, Craig Williams, here in Stafford, Texas, thanks again, and we will speak to you next time.